Okay, first part of homework 6 is, this is the book problem, which was to show that x squared plus n equals mx is the only type of the 6 type of solutions, 6 types of equations to have 2 positive solutions. And well, the way to show this is just to go through all the 6 cases and to actually find the solutions. So the linear equation nx equals m has only one solution. If x squared equals nx, then the 2 solutions are 0 and n. If x squared equals m, then x is plus or minus square root of m. And then the ones that use the quadratic formula, if m equals nx plus x squared, then when we use the quadratic formula, we get in the numerator minus n plus or minus. Well, once you've got the minus n, that means you're going to have one negative solution for sure, and the positive solution is going to be minus n plus square root of n squared plus 4m. And of course, n squared plus 4m is bigger than n squared, so the square root of it is going to be bigger than n. So that numerator is going to be positive. So you've only got one positive there. For x squared equals m plus nx, you get the quadratic formula is the numerator is n plus or minus the square root of n squared plus 4m. So n plus something is going to be positive. N minus, well, n squared plus 4m, as we've seen, the square root of that is bigger than n. So you've got n minus a number bigger than m, so you're going to get something negative. So that just leaves m plus x squared equals nx. So x equals n plus or minus square root of n squared minus 4m in the numerator. Well, as long as n squared, well, it's going to have no solutions, of course, if 4m is greater than n squared. It's going to have one solution if n squared equals 4m, because then you've just got n on 2. And if 4m is less than n squared, then n squared minus 4m is going to be less than n squared. So the square root is going to be less than n. So you've got n plus or minus a number smaller than n. So that means you've got the possibility for 2 possible solutions. And that was the only case that we could have. Okay, so the first of the problems I gave you was this principle of Archimedes, where given any 3 magnitudes of the same kind that can be divided into arbitrarily small pieces, let's call them A, B, and C, with A less than B, there's a force quantity D of the same kind commensurable with C, such that A is less than D is less than B. Okay, so since A is less than B, and C can be made as small, it can be made arbitrarily small, we can find an integer n such that C on n is going to be less than the difference between B on A. Okay, so that's our small little thing, and then we pump it up by m. So then we're going to let there be an integer m such that m times C on n is going to be bigger than A, but less than B. And of course we can do that because C on n is less than B minus A, fits into the gap between B and A. And so then just let D equal m over n times C. Then D is commensurable with C. And, oh, that should have been D. D is between A and B. Oops. Then the second part was showing that polynomials over the reals are non-Archimedean, and that all depends upon the fact that the function x is greater than the constant function 1, since the outputs of x are always greater than the outputs of 1 whenever the inputs x are greater than 1. Okay? So x is greater than 1 because x is greater than 1 whenever x is greater than 1. But no matter how much you multiply the function 1 by an integer n, you're still going to get a constant integer. And so it's always going to be the fact that x is going to be less than n, right? As functions, because x is always bigger than n, since the outputs of x are greater than the outputs of n whenever the inputs x are greater than the input n. Okay, so no matter how much you blow up 1, you can never make 1 bigger than x. So that is non-Archimedean. Okay, so the second question was to show algebraically and geometrically that any square number is the sum of two consecutive triangular numbers. So the picture is pretty straightforward. You just draw yourself a square, you do little dots like this, and you can just then see that you can put a line across the diagonal, kind of like, where is it? Kind of like that, and it's going to split it up into two triangles. And you can do this algebraically because the nth square number is n squared. The nth triangular number is n times n plus 1 on 2. The one before it is n minus 1 times n on 2. And if you add them together, you end up with n squared. So you can show it's quite straightforwardly that the two triangular numbers add up to the square number.